Hello. So, in our study of neural networks, now we will see this in this video the working of a single neuron with a non-linear activation function. So, what are the neural networks or artificial neural networks? These are also called feed-forward networks. So, we can see the forward propagation of the inputs. And the goal of this network is to approximate some function. For example, we have a classifier y equal to fx mapping input x to category y. So this feed-forward network defines a mapping. So this f function f on the inputs x parameterized by w and gives the output y. So it learns the parameters w so that the best function approximation occurs. See, we have drawn this diagram which has this input layer, the output layer, and two hidden layers. So again, here we have now labeled the input layer, two hidden layers, and one output layer. Each of these units resembles a neuron in the sense that it receives inputs from many other units. So consider this, suppose we consider this neuron here. So it is receiving inputs from here, from this one as well, and from this. So all the inputs are going into the each and every node of the next layer. This is the connection which we have drawn here. So, and these units are acting in parallel. That means they all act on the inputs. Feed-forward networks do not have feedback connections. So here we do not have any feedback. These feedback connections, we are not having them. Okay. Where in the networks where we do allow this are called the recurrent neural networks. We'll come to this sometime later on. And similarly, another type of neural networks, the convolutional networks or the convolutional neural networks, CNNs, used for object recognition from photos are a specialized kind of feed-forward network. These are mainly used for images. So, this briefly we have seen what is the artificial neural network, the different activation functions which are used. We have the sigmoid function which is defined in this manner. Yz is equal to 1 by 1 plus e to the power of minus z. And so this is the function 0. And so this function processes the zero point 0.5 value at 0 where z equal to 0 and then goes to the positive side. ReLU is for the non-negative values, it is f equal to y equal to x, see here, and otherwise it is 0. So it is basically max of 0 or z. For all these values, 0 is max, so we get 0. And leaky ReLU allows for some component even when the y value is negative. In the ReLU, for negative y we get 0, but here we are having some component, some value, even though negative. So these are some activation functions. Now, we look into the working of a single neuron. It is a very simplistic uh, example, but it conveys how the computations will go on in every neuron which we take in our neural network. So this is, as per the nomenclature, node 1, layer 2. Okay, so we see these subscripts 1 and the superscripts within brackets is 2. So this is the layer number, this is the node number, and these are the previous layer inputs. So we are seeing two inputs coming from the previous layer. So previous layer was 1. Okay, so superscript bracket 1, superscript bracket 1, node 1, node 2. So input 1 which is coming from the node 1 of previous layer, and similarly input 2. These are going into through the weights W11, C1, so that accounts for 1, and this, the second is for this one. Okay, so we have written here Wij superscript L stands for the weight for the link from node I of layer L to node J of the next layer, Wijl. So this is W111 and this is W221 superscript 1, node 2, node 1 and layer 1. Now come here. So this was the adder portion which we have seen in our McCullough-Pitt model. So this adder is taking the summed inputs. So we have written it here. So this we have written here. Z1 superscript 2, because this node is at layer 2. So this is nothing but A11, which is this input multiplied by the connecting weight, added to the second input A21 multiplied by this weight. So this gives us the adder quotient. Now we go to the second half, the second part of the neuron, which is the nonlinear activation function, the sigmoid function, which we saw earlier. Okay, G of Z12. So this nonlinear activation is applied on this sum which we have got. So G of Z12 is nothing but 1 by 1 plus e to the power of minus Z1. So this is what we get here as the output of this node. So it is node 1, so this superscript 1, and layer 2, so subscript 2. So A12 is the output of node 1 of layer 2. And how we got it? We got it by applying the nonlinear activation onto the added component. This component is obtained from the previous layer inputs passing through the weights. So I hope this description is simple and you get it, how the computations flow through one neuron. We will look at the forward computations through a neural network in the next video. So what we see is the neural network learns its own features. It is taking the intermediate values, outputs AI as its inputs instead of X. Okay, as it goes from one node to one layer to the next layer. Okay, so we have these nodes over here and we get these output from here, and this output becomes the input of this neuron. So this is what we mean by the intermediate outputs or the own features. So the neural network learns its own features for the final computation. Next, we will look into the forward propagation of computations through all the layers, starting from input to the output layer at the final layer. So that we'll see in the next video. So thank you. Thanks for watching.